Hello, today I'm going to be talking about binary search trees. Binary search trees are a node-based data structure. They store nodes in a sorted order by some key. Each node has a left child and a right child. The left child of a node has a key that is less than the node, and the right child of a node has a key that is greater than or equal to the node. Here we have an example of a binary search tree. The top value in the tree, the 5, is known as the root. To the left child of the root, we have a 3, which is less than, and to the right child we have an 8, which is greater than or equal to. On the next level down, we have a 3 with a left child of 2, which is less than it, and a right child of 4, which is greater than or equal to it. On the right side of the tree, we have an 8 with a left child of 6, which is less than it, and a right child of 12, which is greater than or equal to it. Now, why do we use a binary search tree? A binary search tree is much more efficient for many common operations than a linked list or an array is. For example, if you're trying to do a search, the average big O complexity for an array is big O of n, and the average big O complexity for a linked list is also big O of n. A binary search tree, however, reduces this to big O of log n. Each iteration through the binary search tree cuts off half of the data. For example, if we are searching for a 12 in this example binary search tree, in our first iteration, we will look whether the 12 is greater than 5 or less than 5, and since it is greater, we will go to the right child. From this right child, we will also again look to see if the 12 is greater than 8 or less than 8. Since it is greater than 8, we will go to the 12 and we are done with our search. Since we were able to have the data each time, the binary search tree has a big O complexity of log n. The same can be said for insertions or deletions, where the binary search tree also has a complexity of log n when an array or linked list cannot. Next, I'm going to go over how to build a binary search tree using this example set of data. The first step to building a binary search tree is to take your first piece of data and make it the root of the tree. In this example, our first piece of data is 5, which will be the root. Then, with our next piece of data, we need to decide whether it would be the right child or the left child of the root. Since this 8 is larger than 5, it will be the right child of the root. We continue this process until we have used all the data. Our next value is a 3. The 3 is less than the 5, so it will be the left child of the root. If there was already a value in the left child of the root, then we would continue down the tree until we got to a null child. Our next value is a 12. The 12 is greater than 5, so it will go to the right of the tree, but since there's already a value as the right child, it must go down the tree. We next go down to the 8. 12 is greater than 8, and so we will go to the right child again, which is empty, so 12 becomes the right child of 8. Our next value is 6. Our 6 is greater than 5, and so it must go to the right side of the tree. We then compare it with 8. 6 is less than 8, so it will become the left child of 8. Next, we have a 2. Our 2 is less than 5, so it will go to the left of the tree. It is also less than 3, so it will become the left child of 3. Our final value is a 4. The 4 is less than 5, so it will go to the left, but it is greater than 3, so it will become the right child of 3. This is our completed binary search tree. Alright, now I'm going to show you a very simple implementation of a binary search tree in VS Code. We have a class binary search tree right here with data, which is going to be your key, and a left and a right child. The data is initialized as a value that you input, and the left and the right child are initialized to null. The insert method here is what's going to create the tree. In our main method here, we create a tree and we insert in the values that we made the tree out of earlier in the slides. I will have a graphical representation of the tree as we create it over on this side. Our first step is to set the root of the tree to the first thing we insert. So the root equals b.insert of root 5. If we run the code in the debugger, we can see that in our very first iteration, we'll go into the insert method with a value of 5. We'll create a new node with a value of 5, and then immediately go down to a while loop. The while loop will iterate through the tree until we get to a parent node that does not have a left or right child, and we can add our new node as the left or right child of it. Since this is the very first node, the while loop will immediately return null pointer because there is only null pointers. After this, we will go to these if-else statements. If there is nothing in the tree, then we will make the value we have the root. If there is something in the tree, but the value is less than the parent's data, we will make it the left child of the parent. If there's something in the tree, but the value is greater than the parent's data, then we will make it the right child. Since this is the first value, it will become the root of the tree. Next, we will insert an 8 into the binary search tree. We will create a node with the 8 and then enter the while loop. Since we start off with our while loop at the root of the tree, if we look in our x here, we can see that the data is 5 because it is the root of the tree. Next, we will compare our value to x of data. Since our value here is 8 and our x of data is 5, this is not true. In our else statement, we will set our x to x of right. Since we do not have a right child right now, this will be a null pointer, and so that will get us out of this while loop. Now, since we are out of the while loop, we will go to the if statements to see where we want to insert this new node. Since it is not the root, we skip this if statement. Since we are inserting it as the right child, this if statement will not be true either. And so finally, we will skip to this one and insert as the right child. Next, we are inserting a 3. Again, we create the node with a 3, and we start at the root of the tree. Our while loop loops through, and eventually we get to the bottom where we realize that this 3 will need to be inserted as the left child of our root node. We will continue through this process, inserting each node as the right or left child of the bottom node. I'll speed it up so you guys don't have to watch each part. Alright, I want to go through one of these bottom nodes just so you can see how it's different, how it iterates through the entire tree. So we're going to go through the insert of root 2. So first we make a new node with the value as 2. We set our x and y equal to the root node, which is still going to be our 5. And then we go through our while loop, where if value is less than x of data, we go x equals x of left. Since value is 2 and that is less than 5, we're going x equals x of left, so we're going to go down the left side of the tree, which will bring us to the 3. From the 3, we will continue, and if value is less than x of data, we'll go down the left side of the tree, which will now bring us to a null pointer, taking us out of our while loop. Then we will compare our y to the node to see whether it needs to be the left child or the right child. Since our value is less than y of data, our new node will be the left child of the 3. Once we finish going through this, we will have built a binary search tree with all of these values, just as we did in the visual representation. I hope you were able to learn something about binary search trees from my videos, and thanks for watching.